All right, so what we're looking for are extreme values of n. So as n goes out to infinity, and that's what we did here. We tested one, two, three, couple, a few, maybe more than that, maybe less than that, in order to get a sense of what's going on. Visually, sometimes that's the case. All right, but sometimes all you need to do is just find the limit. All right, you could list out a few options if you want. You can plug in a 1, a 2, a 3, but I want to know what's going to happen to this sequence for large values of n. So a strategy would be to find the limit as n approaches infinity of n plus 4 over 3n minus 2. All right, so basically asking, will this sequence ever level off anywhere? All right, so what we do is we find the limit of the n behavior model. When you're dealing with a rational function, let me just make that a little better. You're going to find a limit of the n behavior model, which is what you would get if you were to divide the term with the highest power on top by the term with the highest power on the bottom. Simplify that out, it goes to 1/3. So you're finding the limit as n approaches infinity of 1/3, which is 1/3. All right. Oh, vertical asymptote? Oh, no, not at all. Because we're only looking for extreme values of n. So unless the vertical asymptote itself was somehow at infinity, and I can't even conceptualize how that might be the case, it would not have any impact. I'm not really sure why I had to walk over there to tell you that.
So do you know anything about the number 5? That you said in this case, well, actually, you're looking for the number 1. No, you get number 5. So we taking, so actually, yeah, we're going to see number 1. So we're going to say that the 1/3 is going to be a series that's going to, basically convert, right? But why number 5? Because we have that piece of something that is not defined. So we still.
Because when you're looking for convergence or divergence, we're only looking for the extreme. So if I were to create a graph of some kind of rational function, I don't know, just going back to Calc 1, say you have the limit as x approaches infinity. It really doesn't matter. I'll just say 1/x to keep it simple. All right. So we have a vertical asymptote at 0. We'd have graph existing over here. We'd have graph existing over here. I have a little extra fluff that I don't need. All right. So out over here is where infinity is. What I'm doing when I'm finding the limit is I'm tracing the path along the curve, starting on the left-hand side, going to the right-hand side towards positive infinity, and just asking myself, where's y go? All right, that's a Calc 1 limit. So in this context, yes, there is a vertical asymptote at x equals 0, but the big question would be, why the hell do I care about that? Does it matter? I care about what's happening to the graph as I go out to positive infinity. This is nowhere near positive infinity. There's not some barrier you can't get past. You just can't be in touch. You can't make contact with x equals 0. So if I'm going out to positive infinity, I'm only dealing with points along this curve. The same idea with a sequence or a series. It's just I don't care about any of this stuff because the n value has to by definition be greater than 0. All right. So all of that's irrelevant. So if it was this relationship, the asymptote would naturally not be relevant. But if I had a bunch of points, I'm working on a sequence. I have a bunch of points, and it's following a pattern like this. Let's say it's oscillating back and forth. Nice wide margin early on. And then eventually it starts getting closer and closer to a particular y value. All right, some might say it's converging upon a particular y value. But let's say, for example, along the way, I have an open circle, meaning a point that doesn't exist. Let's say I'll put it right here. Okay, so along the way I have a point that doesn't exist, whether it's a point that's continuity or a vertical asymptote. It doesn't make a difference because I don't care about any of these points. I care about what's happening for extreme values of x. All right, is it converging on a particular y? In general, yes, down the line. But does it matter if there was a whole asymptote jump? No, not at all, because it's not relevant to the extreme value of x. Right, so that's what's happening for this question here. We tested a few values to see what was going on, to get a sense of it. Turned out one of them didn't exist. Is it an asymptote? Is it a whole? I don't care. Because I care about what's happening as n gets extremely large. All right, if you look at that value of n equals 3 as some kind of hurdle, okay, you jumped over the hurdle. Now continue. All right, so once you get past that, it's just a question of what's really going on within the nature of the function, right? And so what we determined here is that, what we determined was that it didn't matter what the tangent was going to be because this was going to 0, so the whole thing had to converge to 0. All right, and you can look at the graph, just put it in as an equation, a function in terms of x, and you'll see, just make sure you're in radian mode, you'll see that the graph is converging on a particular number for extreme values of x. We don't care about what's happening at 3, we care what's happening about like at 3 gazillion. All right. So then we take a look at something like number 2. Now, you get a lot of possibilities when it comes to taking limits. All the skills that you learned in Calc 1 could come into play. You can...
So number 1 is just convergence of 1/3.
Yeah. Convergence to 1/3. Now, and again, this is not to dismiss what I was talking about last class. You could very easily, I think, plug in some values for n and see what's going on. Once you do, I think you're going to be in pretty good shape. I'll do it with the analytic approach, just because I know lots of people like that. Limit as n approaches infinity of n squared over e to the 4n. Now, if I did that by direct substitution, so if I plugged in an infinity for n on top, what would I get? Infinity. On the bottom? Infinity also. E to the infinity would be infinity. So this would be infinity over infinity. All right, so that's good news. It's not an answer, but it tells us how to go about getting our answer. Because if you have 0 over 0 or infinity over infinity, then good old L'Hopital's rule works. All right, which means that I could take the derivative of the top, a little refresher on that, slash maybe your Calc 1 teacher skipped it, I don't know. Derivative of the top, it's not quotient rule again, it's just simply take the derivative of the top and divide it by the derivative of the bottom. Seems to actually break rules of differentiation, but it works. All right, plug it in, plug your infinity in for n, still infinity over infinity. That's great news. It's not the answer, but it tells us how to go about getting the answer using L'Hopital's rule. Deja vu. Take the derivative of the top, divide it by the derivative of the bottom. Red. Substitute. Oh, not plugging anything in on top, right? So leave it at 2. On the bottom, infinity, constant over infinity equals 0. All right, this is a case where I wouldn't have done it analytically, but I wanted to show you because I would just look at it and say, well, bottom's going to get bigger, faster than the top. And so it's going to
like E, like a constant to the power of infinity is a bigger infinity than an infinity to a constant.
exactly. Exactly. And it's also, there's justification for any behavior model rules working. Because if I plug in infinity in for this, I'm getting infinity over infinity. But if I take the derivative, I get 1 over 3. You do it that way. This also ends up being the case that if you divide the two and sub in, it works. So a lot of those pre-calc shortcut rules that didn't have any seeming explanation comes out through L'Hopital's rule. And so that's pretty cool. Number 3, it's a goofy kind of problem, but again, we're looking at the same concept over and over again. What's going on with the function as you go out to infinity? All right? So it's a valid, meaningful question, but sometimes you can just consider it and come up with your answer. All right? Cosine functions. I don't care what's inside the cosine function. The cosine is going to bounce back and forth between what? Two numbers. -1 and 1. All right? So some number between -1 and 1 is going to be on the top. When you get out all the way to that magical land called infinity, even though it's not a land, it's a place that's in motion, so it can't be like one place. But anyway, some number between -1 and 1 will be on top. What number would be on the bottom? Infinity. What is a constant divided by infinity? 0. This thing is going to 0. All right, you could do it that way. You just reason it out. I mean, if you like the squeeze theorem, I mean, I got an analytic approach for you. It's fun. I know, again, cosine has to be between -1 and 1. Also known as the sandwich theorem. We talked about it last class briefly. But I find that in a lot of cases, the sandwich or the squeeze theorem could be bypassed with just a smidge of common sense. And lacking common sense, graph and calculator, supplement your lack of common sense with the calculator. How about that? All right. So I have a relationship that I know exists. Cosine is always between -1 and 1. All right, that's cool. I need cosine over the root of n. So I'm going to divide by the root of n everywhere. So then I'll take the limit of each part as they go out to infinity. So I just kind of little shorthand notation here. I'm saying I'm taking the limit as n goes to infinity for each little piece here. Rather than writing limit as n goes to infinity for the first part. So limit of this less than or equal to the limit of that, less than or equal to the limit of that, which is just, it has writer's cramp written all over it. The limit as n approaches infinity of this would be what? 0. You're going to have -1 over 0. Okay? The limit as n approaches infinity of 1 over root n would be what? Also 0. So the limit as n approaches infinity of cosine 5n squared will be squeezed or sandwiched in between 0 and 0. So pretty safe bet it's 0.
Why is the constant over infinity 0?
Because as you increase the denominator, so as you're dividing I'll just use 1 by a particular number, you get a fraction, 1 divided by 2. Increase the denominator, the fraction gets smaller. If you increase it infinitely, it becomes infinitesimal. All right. It's actually a byproduct of that graph y equals 1 over x. This guy over here, how it has an asymptote, a horizontal asymptote at 0. This is actually the visual or physical representation of that idea. It's just, words, apparently. So this is converging to 0. All right. So if I were to graph this function, you're welcome to do it. I mean, you can just pop it right in. Just and take a look in your home screen or your standard viewing window and see if you have a clear vertical, horizontal asymptote. If not, then go to your table, keep scrolling, or you can change your table settings. All right. So what I think I'll do actually at this point maybe is move on, because if you had, and I'll come back to this next class, there's 3 of them. If you had trouble with this, then you probably want some time to kind of look at it again. And so, and also maybe what we covered tonight will shed a little bit of light on some of this stuff. All right, so this is 1, 2, and 3 on page 73. Set.